All right. So 7.1 Intro to Differential Equations. As I alluded to with 17C, you kind of pick up on this idea of differential equations, but you just do two of them at the same time. And all of the 17 series, in some parts of 17A, B, and C, they're all kind of building these ideas that we eventually use. They all kind of come together in 17C. So what I wanted to do to intro what a differential equation is actually take you back to 17A, because we didn't maybe realize it at that time, but they were kind of setting us up for the idea of a differential equation. So if you remember from 17A early on, we could talk about a sequence that might look like this, where n, let's say n is the population at some time t of something, a species, bacteria, whatever. And this formula will tell you the population. And in this, back in 17A, the way this worked is we just got a sequence of numbers. In fact, let's just generate some of those terms. So we would start with like, well, we could start with 0, I guess, and then go 1, 2, 3, 4, let's say. And if I just plug this in, 2 to the 0 is 1. That says my population starts off at 3. When t is 1, that's 3 times 2 is 6. When t is 2, it's going to be 2 squared, so that's 4. This would be 12. This will be 8. That's 24. And then 2 to the 4th is 16 times 3 is 48. And so if you plot these, I'm not sure I'm going to put a scale on here because, well, I'll put the original one. So when t is 0, we have a population size of, let's call this 3. When t equals 1, it's 6. I'm going to guesstimate and say that's about 6. T equals 2, all of a sudden it's now double that, so it's 12. It's up here. I want to be able to fit in, you know, the next data point because it's going to be 24, and that's really big. And so what you see is a pattern of data points that are increasing. So what is this describing? What kind of a growth does that? It's certainly not linear. That's exponential growth. Yeah. So this particular sequence would model exponential growth. And what I also want to remind you of is when we talked about sequences, we figured out that there were a couple different ways to denote a sequence. This is what they just call an explicit formula. All that means is if I decided I wanted to find the population when t is 20, I can do it. I can just plug in 20 for t and it'll tell me the population. But another way to describe a sequence like this is with a recursion. You may recall from 17A. We didn't spend as much time on this, but what the recursion is doing is it's describing the same pattern of numbers, but it's telling you how to get from one term to the next. Remember that n sub t plus 1 represented how do you get to the next term. And this would be the previous term, the term you were on, the previous term. And that is pretty obvious here, right? Like, how do I get to the next term? What's happening from 6 to 12, and then from 12 to 24, and then 24 to 48? This population is doubling, right? Doubling. And so if I had my previous population size, how do I find the next term? I could just multiply my previous population size by 2. This is describing the doubles. And then you may remember, like, no recursion is complete unless you state an initial condition, because you have to know where to start. And so you would have to define your population size at t equals 0 was 3. That was given in the problem. And you may even remember, besides recursion, another name for a recursion, I'm pretty sure Professor Martinez described it this way, is a difference equation. Do you remember that? A difference equation? And the thing in 17a is these were sequences. These were just dots, just points here, right? But if I modeled this same kind of growth with a continuous function, if I were going to put like a graph in there, in other words, not just talk about the population at 1, 2, 3, but anything in between, you know, when t is a half or 0.9 or 1.7, right? If this was a continuous function, this gets us to the idea of a differential equation, kind of like a difference equation, but a differential equation. And this is what you're studying right now in 7.1. And so dn dt, we recognize that as a derivative from 17a, but what that's basically saying is saying, I think at the end of 17a, we talked about dn represents the change in the population, change in n, right? And this represents a change in time. And so together, this, you could read this as, how is the population changing with a change in time, right? How is the population changing with a change in time? And isn't that kind of like what this is saying? This is saying in the next time period, how is your population changing? It's double the previous time period, right? So in reality, this recursion idea really is kind of a model for a differential equation. For this same exact example I gave you, the differential equation that would model this would just be 2 times n. Do you see the similarity? It's exactly the same. Because this is telling you the change in my population each unit of time is double whatever my population was before. Change in population is, okay, we'll just double the population each unit of time. That's what that's saying. And then you would do the same thing. Well, okay, that's good, but I need to know the initial population size, which in the original problem was stated to be 3. Okay, so that's all a differential equation is. It does involve a derivative. This time, we weren't thinking of derivatives here. We were just thinking of that as a sequence, but this is now a derivative, but it is describing the same thing. And the way this works is in 7.2 and 7.3, in the coming sections, we'll actually work on how to solve these differential equations. As you might suspect, if I wanted to solve, if this is the derivative of n and I want to solve for n, I'm going to need an antiderivative. And of course, that makes sense. This is 17b, right? It's all about antiderivatives. But we're not quite, 7.1 doesn't really get into solving them yet. It gets into more like, well, first of all, terminology, and then also like thinking about what a differential equation is describing. So this section is very ripe for quiz and test questions that you might see on the next test because they're conceptual. A lot of these questions, not these right here. Right here, we're just talking about some definitions, but you'll see in a second, I've got some good examples of that. Bring it down, yeah. There we go. And there's 3, the book talks about, there's more than this in reality, but there's 3 types of differential equations they'd want you to just be able to identify. Put this here. And the first one, the good example we just did here, is called an autonomous differential equation. Because what an autonomous differential equation means is that, think about it, that if you're an autonomous person, doesn't that mean you're kind of, you take care of yourself, right? You depend on yourself. You can do things on your own. You're independent. And this is kind of what it's saying. It's saying the growth rate of my population if n is my population size, depends on the population size. So its own population controls how fast it's growing. It's not a function of anything else, right? So how can I write that in words? The growth rate of n depends on itself. That's the characteristic of an autonomous differential equation. Now, you could also, maybe a different population is growing, and it doesn't necessarily depend on the population size, it just depends on time, right? As time increases, this is going to affect the population. So that's called a pure time differential equation. So the growth rate depends on time only. Growth rate, let's put rate of n depends on time only. And then if you could certainly think of populations whose growth rates depend not only on its population size, but also on time, right? They're functions of both of those. And they just collectively call that a mixed differential equation. So that just means it depends on both. Both the population size and time. That's a time, believe it or not. So this is just terminology. I don't think these are quiz questions or anything. That's just, you're going to see in the problem statements like, consider the autonomous differential equation, and everybody's going to go, what the heck does that, what does that mean, autonomous, right? So this is just so you know what they're talking about when they describe the problems. And there's two population growth models that you're going to do all kinds of differential equations that are different models, in many cases about populations, how they grow. But there's two big ones that you should know for this class. And again, I'm thinking of 17C. The ideas we learn here are built on in 17C as well. You're going to want to be familiar with these growth models. And the first one is the one we same example here. Where's my first page? My first page, I had this differential equation, dn dt is just 2n. That's an autonomous differential equation. And we saw that that really just is describing the same thing as a sequence like this, which is describing exponential growth. And that would be true anytime you get a differential equation where it's dn dt is equal to some constant. K in this case is a constant. Times n. That's going to be modeling exponential growth. I left some empty graph here. So that's just something where it's like, we know what that graph looks like. Something like this. Also called, we'll sometimes refer to this as unrestricted growth, right? The idea of exponential growth is there is no limit to how big the population can get. While that might be true if you're talking about, bacteria cells or virus cells and stuff like that, because that's not really true if you're talking about like species of animals or something like that. But there's sometimes when that's a good model for something. And the solution to this, I told you we're going to work on solving these later, but you already know this. This is an exponential growth graph, and many of you are familiar with this equation, CE to the KT. If you remember y equals CE to the KT, that describes exponential growth. Only it's going to be n equals CE to the KT if I use n as my variable. So this is the solution. And then the other one trying to remember if we did. I know there it's in the 17A curriculum. I don't remember if we spent a lot of time on this in 17A last quarter. I don't think Dr. Martinez did, but a lot of times in 17A, they will spend a lot of time on this from a sequence standpoint. Another really, really important growth model is called logistics growth, also referred to as restricted growth. And this is the idea that, you know, like, again, if you're thinking of a growth rate of a species of animal or something instead of bacteria, you know, maybe as a population is getting started, it can begin to look like it's exponentially growing. But then due to other things like competition for resources, you know, all kinds of factors, there may be some kind of ceiling of how big the population can get over time. And as it gets closer to that population carrying capacity, is what we call it, the growth rate will kind of slow down and sort of settle on whatever that maximum population is. And we usually use, I don't want to confuse it here, like capital K for that, which is referred to as the carrying capacity. Carrying capacity. Boy, my writing is getting bad. And I already saw it in your lesson on Wednesday. There's plenty of problems in the book on this. So you should get familiar with this because there's going to be a lot of problems on it. The general formula for that, like your general differential equation, will always look like it kind of starts off, except I'm not going to use K here because I don't want you to confuse it for that one. Some constant like R times N. It starts off looking like exponential growth, and that's referring to like this part looks just the same. But as we get closer to K, like this distance right here between whatever your population is here, right, at whatever value of T is, this is my population size at this time. This distance right here is actually it's actually K minus N, but we'll yeah, let's just do that. And what happens is as you get closer to that, this causes the growth rate to slow down. And so there's this extra factor. It's actually not quite like that. You know what they do? Here's what they do. I'll explain this. If you took K minus N and divided both of those by K, you end up with 1 minus N over K, which is this term right here. And so your differential equation that describes logistics growth will always look something like this. And so if you spot one, I've got one coming up here, you'll know what that denominator means right here. That is the carrying capacity. That's your theoretical maximum population. And I just left this blank here. The solution to this is rather complicated, so I'm just going to put, we'll see later. So here we go. Yeah, perfect example here. Let's say I have a population that's growing according to the model dn dt equals 1.3 n times 1 minus n over 500. Do you see that's just a perfect match with this form? So this is describing logistics growth. Which is also an autonomous differential equation, isn't it? Nowhere on the right side do you see t. It's all in terms of n. The growth rate of n is just a function of its own population size. And one of the things we do that we're going to want to start to do with differential equations is finding what we call equilibrium points. Equilibrium point, what does that kind of sound like? If something's at equilibrium, then it's not changing, huh? Things are not changing. But we've already described dn dt as how fast the population's changing, right? This is the rate of change of population. Rate of change of n. So if equilibrium means I want to find where things are not changing and dn dt is the rate of that which things change, what do I want to set dn dt equal to then? And this will be true for all differential equations. You're going to get, other than, not just logistics growth. But if they ask you to find equilibrium points for a differential equation, this is the rate of change, and we want no change. So we're going to always set our derivative equal to 0. So if it's not changing, that means we're going to set dn dt equal to 0. dn dt equals this mess. So I'm going to have 1.3 n 1 minus n over 500, setting that equal to 0. And it's, it's already in factored form, like when you're factoring a quadratic, finding out where it's equal to 0. So from this term right here, what would make this term equal to 0? Equilibrium points, by the way, are special population sizes. So I think what the book does, I'm trying to be consistent. When you're finding an equilibrium point, they'll put n hat on top of it. That just means it's an equilibrium point. What makes this part 0? That would be if n is 0, right? And what would make this 0? So I could say this, there's one possible equilibrium. Or now you can do the algebra, just think of it this way. If I've got 1 minus something equal to 0, what would this numerator have to be? This has to be 1, doesn't it? So what would n have to be there? It's going to have to be 500. Yes. Okay. Now, more terminology that you're likely to see here in the coming sections here. If you're talking about if we've got some context here, like maybe I'll say a population of, I like to use squirrels because there's a lot of squirrels on campus at UC Davis. So if I had a population of squirrels that was growing according to this model, my equilibrium population sizes are 0 and 500. So what does that mean? This means if my population of squirrels is 0, it will never change. Well, how many people think that's like, duh, of course. If I don't have any squirrels, I'm never going to get any more squirrels, right? That's like, okay, that's true, but that's not really very interesting. And so for a lot of times when you get an equilibrium of 0, we call this a trivial equilibrium. Trivial just means it's not really that important. It's not really interesting, oftentimes associated with 0. Whereas this is, to me, is interesting, right? Because what this is saying, this would be a non-trivial answer. And what this is saying is if my population, I'll put, if my population of squirrels gets to 500, it will stay there. It will not change. It will, according to this model, right? It will stay at 500. There, by the way, I told you this is all related to stuff in 17A. Does anybody remember? There's a term in 17A with sequences that we found that where if you're at that value, it never changes. I think maybe not, because I don't remember if Dr. Martinez explained it that way, but in 17A, these were called fixed points. Fixed points in 17A. That's just a side note. You don't have to write that down. But yeah, when you're doing sequences and you find your fixed points, those are the places for which the sequence never changes as well. Now think about why this makes sense is, we know, and that's why I think you should be familiar with this model. We know what this graph should look like. If it's really logistics growth, it should look something like this. And so what that's saying is if my population gets up to its carrying capacity at 500, it's just going to stay at 500, right? It's like an asymptote. It's never going to change. So that makes sense that that is an equilibrium point. All right, next question related to that is, if my population is not changing at those values of n, at other population sizes, that must mean that n is increasing or decreasing. If n was increasing, what that means is the derivative, the rate of change of n, dn dt, must be greater than 0, right? It must be positive. You can even think of that when we were graphing functions at the end of 17a. When does something increase? It's when the derivative is positive, right? And when is it decreasing? That would be when dn dt is less than 0, when it's negative. So to answer these questions, I would do it really just like you were doing this in 17a. This is the derivative. This d is dn dt. We know it's equal to 0 at these numbers. You could almost think of those as like critical numbers back in 17a. I would just put these on a number line. Let me so below the number line is my population size. Above the number line, I'm going to collect information about my derivative, which was 1.3n times 1 minus n over 500. Let me. And 0 and 500 are places where dn dt is equal to 0. So those would be like my critical numbers. And what you could always do is just pick different values for n, pick test numbers. So if I let n be, you don't even have to make it close. If I pick something bigger than 500, like let's say 1,000. Why is this not looking too focused? There, that's a little bit better. And I run that through here and here, this will be positive, but if n is 1,000, this is going to be 1 minus 2 is negative. A positive times a negative is negative. And so if dn dt is negative, it means my population size will decrease. If I pick, let's say 100, this will be positive right here. 100 over 500 is 1/5. 1 minus 1/5 is still positive. So I get positive. Population's increasing. Now, I know if we're talking about squirrels, this doesn't make any sense. But if I had, in a different model, maybe we could allow negative numbers here. So if I had like negative 100, let's say, this will be negative. This will be positive. Yeah, that's right. And a negative times a positive is negative. So this would be decreasing. And what that part of this, at least this part, should make sense, because again, if you envision this part's optional, but if you would think about logistics growth, like if this was a graph of my squirrel population over time, we know there's a carrying capacity of 500 squirrels. And what this is saying is, if my population were to somehow jump up here to 1,000 squirrels, what it would do is it would decrease. If my population got up to 1,000, it would decrease. And the way it would decrease is it would slowly settle on this population of 500 squirrels. If my population was only at 100 squirrels, this says that the population would increase, and what would happen is it would increase until it gets to that carrying capacity of 500 squirrels. So that's what my growth curve would look like. Yeah, and then what this is saying is if I had negative 100 squirrels, my population would just go down even further in the negative territory. So these could be thought of, and we're going to be getting to this, these are solution curves that you could draw based how do I generate that graph? Based on looking at this, right? Just by seeing what happens to the population size at different values. I think you'll see some of this on Monday's class in Dr. Burke's class. So. Okay. And then I've got a series to finish this off. I've got a bunch of problems here, but there's a lot of these problems in 7.1 where it's all about like visualizing and analyzing the differential equation to see if you could predict what the solution would look like, what it would have to look like based on the form of the differential equation. And like I said, this I think is very ripe for the type of questions I usually am noticing from Dr. Burke are more thinking questions. You know, there's some exception. I think the last test was, well, I don't know, I haven't seen it, but if it's just find the volume of this, find the area of this, that's not as much as, but this section of the book is very notorious in past quarters for not just asking you to solve it, but to actually to write and analyze things and make predictions based on the equation you have and not on actually solving it. Okay, so yeah, so I've bought enough time here. So the way to think of this is when they write y prime, let's pretend this is saying the growth rate, y is a population of something. Maybe it's squirrels again. Use squirrels if you need something. And it's always going to be, if we use it in a realistic situation, it's probably always going to be, how does this population change over time? And in this case, it's just it's an okay, let's classify this. My growth rate is only dependent on y, so this is autonomous. I'll switch to blue here. But what does this kind of say in words? This is saying the population growth rate is the negative of y is my population size of my population size. So in other words, example, if my population is 100 squirrels, this is saying my growth rate is going to be negative 100. That means I'm going to be losing 100 squirrels per unit of time. I'm going to lose them all in the 1 unit of time here, right? If I have my 100 squirrels, this would be squirrels per unit of time. And so if you had to predict what a solution curve would look like, if I had some initial population here, right? Maybe it's 100, maybe whatever it is. Over time, what's going to happen is your population is going to decrease. By the way, okay, here we go. Wait. Sorry. How many people see this equation as having really the same form as this one? What's my value for k, though? This is like dy dt equals negative 1y. That's a special case like this. And we know the solution to that is an exponential, some kind of an exponential equation, which would be ce to the negative, right? It's kt, so ce to the negative 1t. What does that describe in your experience? Exponential decay, doesn't it? Remember that? A lot of times we do it with radioactive materials and stuff. But if you talk about population, that means your population is going to decrease exponentially. It's going to go down like this and approach zero. questions on that? Does it make sense? Maybe I'll just make a note here. So population will decrease over time. And I think for something like this, I mean, if you didn't pick up that it was decaying like an exponential function, if you just had it going down, that's probably enough, right? All right, let's try another one here. While in reality, I think for most of the applications, your, what do you call it, your independent variable. Yeah, I've been using N and Y. This could be like the population size. It should be a function of time, but the book uses interchangeably. They'll sometimes just call it X, but you could envision X as kind of like time. So this is saying dy, I'm going to stick with X because that's the way the problem is written, but think of that as how your population over time is e to the x squared plus y squared. So this, how would you classify this? Is this autonomous, pure time, or mixed? I'll just put pretend x is t when you get these. Yeah, this would be a mixed one. This is a mixed because it has both x and y in it. And then you would just really, what kind of like this one, you want to ask yourself, well, what kinds of, if this is telling me how my population grows over time, what kind of numbers will I get out of this? That's a wide open question, isn't it? How about this? Could you get any negative values for this? If you're doing e to the x squared plus y squared, is it possible to get, yeah, you're never going to get any negatives, huh? For one thing, this is always positive. For another thing, e to anything is always positive. So I'm going to put note, this is always positive. And so what does that mean? So my solution for y, if the growth rate's always positive, that means my solution y should always be increasing, always be increasing. And maybe another thing to note is what happens as x and y get really big? As x and y get really big, this gets infinitely big, right? I'll put also note that dy dt, dx, whatever, dy dt, if I plug in a big enough x and y, even negative values, right? If I plug in negative 10 million and square it, this is going to be infinitely big. So my derivative will approach infinity as, one way you could write this is you could say the absolute value of x and the absolute value of y approaches infinity. What that's covering is not only when x and y are both positive, but if they're negative and you took the absolute value and those got really big, dy dx would approach infinity. So what that means is as we move to the right, you would expect this slope to get infinitely steep, really, really steep, really, really steep. Well, how about this? We might as well, what about at 0? What if x and y are both 0? If x equals y equals 0, then notice that dy dx is equal to e to the 0 plus 0, which is just 1. So you could interpret that when x and y are both 0, like right here, you have a slope of 1. Your solution is going to be rise over 1, should be about a slope of 1. But what's going to happen is, as we, like we said, as we move here, it's going to get infinitely steep. And same thing over here. As you move over here, this is going to get infinitely steep. It's always increasing and just getting steeper and steeper at the ends. Let's try one more of these. I think these are problems from the book too. I don't remember the numbers, but well, maybe I. Actually, they're close. They're not. I made these up, but they're very closely resemble problems from the book. So yeah, I think, using this as a guide, I think maybe what things to notice is ask yourself like, okay, what kinds of numbers would this always be positive, negative, both? But once again, I would say that because whatever you're plugging in for X and Y, you're going to square it and then add one, there's no way this could ever be negative, right? So I know that my dy dx is always going to be positive again. But let's ask ourselves kind of the same question. Well, what would happen if X and Y both got really big? Absolute value of X and absolute value of Y approach infinity. What's going to happen to dy dx? Yeah, remember this goes back to like 17a. If X and Y get really, really big, this denominator is going to get really, really big. And you're going to have 1 over infinity, which is going to approach 0, right? I'll put approaches like an arrow. It's going to get closer and closer to 0. And then maybe I'll do the same thing as like at x equals 0. Let's get like a baseline here. At x equals 0, y equals 0, right at the origin, what would my slope be? It would be 1 over 0 squared plus 0 squared plus 1, which is 1 over 1, which is 1 again. So I could say, I know right here at the origin, my slope's going to look like the line y equals x. But this time, as we move out in this direction, instead of getting infinitely steep, it is always going to stay positive, but my slope's going to approach 0. You could envision that kind of like this. As if there's like an asymptote here, right? At some point, there'd be like an asymptote where your slope is it's still positive, but it's starting to approach 0. And same thing over here. You could think of this. If X and Y are both big and negative, this is also going to approach 0. So my solution curve might look something like that. I said that these types of problems are very ripe for like, test and quiz questions to see if you are following along. What I'm not so sure about is if they would ask you to actually sketch the whole graph. But what I could totally see is giving a differential equation and giving like 4 different possibilities, and you have to pick which one matches up, right? Which one's the correct solution curve for this differential equation. And so this is another similar to another problem in 7.1, where just think of it as like here would be how you could rule out things. Like if you had a bunch of graphs to choose from as possibilities for what the solution curve to this would look like, how you could rule things out and arrive at the correct solution. We'll have to do one at a time. I can't fit them both here. I know it takes a minute to write these down. But the question here is not graph it, but I've already told you, this solution curve is not a solution curve for this differential equation, but you have to kind of explain why. How do you know that can't be the solution curve? And so good things to think about, good things to think about, just like we did before. What do we know is always true about e to any number in terms of positive or negative, no matter what y is? What kind of a number will you always get? Agree, right? Positive, yeah. Even remember, even e to a negative number, e to the negative one is 1 over e. That's still positive. So you're guaranteed this will always be positive. And because this is squared, this will most of the time be positive. So if my derivative is positive times positive, then it's that what that's saying is my solution should always be increasing, which this is. But I said almost always be positive. What's the one value of t where it's not positive? Exactly. If t is 1, then this whole thing becomes 0, which basically means if you think about what we were doing earlier, if I were to set this equal to 0 to find equilibrium points, e to y is never going to equal 0, but this whole derivative will equal 0 when t is equal to 1. And if my derivative is equal to 0 when t is equal to 1, what I should be seeing, so we should see no growth. In other words, solution curve should be horizontal, right? Remember when you set the derivative equal to 0, that's like a critical number, you should have a horizontal tangent line. Solution curve should be horizontal at t equals 1. But what are we seeing at t equals 1? We're seeing the slope is not, right? But it is not. So this cannot be the graph. This cannot be the solution curve. And then I got one more for you, and then we'll be done here. No, I'm sorry. I'm gonna. There, I can fit that in. Here we go. Oh, and I'll rewrite the differential equation right up here. dy dt was e to the y times t minus 1 squared. So what's the problem with this one? Yes, this equals 0 when t equals 1, so I should have a horizontal flat place, and that's exactly what happens when t is 1, right? T is 1, I do have a horizontal. But what part of our differential equation would this not agree with? Yes, yeah, exactly. We also did agree that other than t being 1, we should always be getting positive values for this, in which case my solution should always be increasing, right? So we'll just say for t not equal to 1, dy dt is positive. So solution curve should increase. As long as I'm not at t equals 1, for t not equal to 1. But this part right here is decreasing, right? But curve is decreasing. So this cannot be the solution. All right, so how's that? You bet, yeah. I'll go ahead and stop the recording.